So section 4.4 is the fundamental theorem of calculus. This is one of the most important parts of this semester. So that's why we're spending 3 days on it. Okay, fundamental theorem of calculus, you got to know it really well in order to solve all your other problems that would come after. Okay, so there are 2 parts to this theorem. We're going to explain each part in detail, but we're going to do just the first part today. Okay, so suppose that f is continuous on AB, so fundamental theorem of calculus, in other words, FTC. So we'll say FTC a lot. Fundamental theorem of calculus. There are 2 parts. The first part says, so I will explain this in detail. For now, just copy them down. The first part is integral from a to b of a function f of x dx is equal to capitalize f of x from a to b, and we write it with a line, and I'll explain what that line means later, which is equal to f of b minus f of a. And then f of x is the antiderivative of the little f of x. So, like I said, don't worry about what does this mean. I will explain this in detail. Just copy it down for now. Yes. So there are 2 parts to FTC. So this is the first part. The second part is d dx, so the derivative of the integral from a to x of f of t, oops, I said t, dt is equal to f of x. Okay, so this is the second part. So we're going to just go over part 1 today, and then we'll do some practice tomorrow with it. And then the third day, we're going to go through part 2. Okay, part 1. What does this mean? Okay, kind of a proof, but mostly just to explain to you what it actually means. Okay, so part 1, if you look at the equation here, integral from a to b of f of x dx, just that part. What does that part mean? The area under what curve? F of x from a to b. Good. All right, so let's try to draw a picture. So f of x from a to b, and we are trying to find this area. So that's what the integral means, right? What it's saying is it's equal to f of b, that f is the big F, minus f of a. And it tells you that f of x, the big F of x, is an antiderivative of the little f of x. So it's a function of, it's an area function because it's the antiderivative. Are you guys with me? So the big F of x just means area, right? Because it says it's the antiderivative, so it must be the area. Okay, so area of what? Area of this minus this. So what this means is we have this function again, f of x. Big F of b means the area all the way up to b, from all the way to the left. Everything from b all the way to the left. Okay? Minus the area. All right, so it's equal to big F of b minus big F of a. That is the area from forever to the left up to a. Right? This makes logical graphical sense, right? This amount of area from a to b must be this much area minus this much area, right? So that's all it means. Okay, so that's it. That's what the derivative FTC part 1 means. Yes. 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 All right. Let's look at an example. So okay, so this graph here is f of t. And they tell you that g of x is such that it's from integral from 0 to x of f of t. Okay? G of x is the integral from 0 to x of f of t. So let's evaluate all these functions. So g of 0. G of 0 means when x is 0. So this is the integral from 0 to 0 of f of t dt. What does this equal to? 0. Good. When you integrate from the same point to the same point, there is no area, it's just 0. Okay, next, g of 1. G of 1, again, just means put 1 in for x. So 0 to 1, f of t dt. All right, so what does that actually mean? G of 1 means what?
Just from 0 to 1.
The area from 0 to 1, right? So what do you guys think that is? 1. Yes, so just look at the graph and evaluate. G of 2. Integral from 0 to 2, f of t dt. Good. G of 3. Oh, this one's a little, you have to kind of estimate because that's a curvy graph.
Can we plant flags first or 4 first and subtract it?
I don't think that would help that much because we still don't know how much that is, that little curvy thing.
So what do you do?
Estimate. 3.5? I like it. All right. G of 4, integral from 0 to 4, f of t dt.
4.
What?
That was 3.
3. Remember, below x-axis, subtract. Okay, G of 5. 2. Yes. We subtracted out this part and this part, so it's just 2. Okay, good. Okay, look at it. Any questions before we move on? Oh, just kind of try to do take this part and put it over there, kind of put it together. Yeah, there's nothing you can do. No, yeah, we don't know what that curve is.
And we're allowed to do that on the test?
Yes, of course. Yeah, if there is no curve, that's given to you.
Okay.
Okay, next. Let's actually solve. All right, so now I'm going to show you how to really solve an integral. So this is kind of the, kind of like derivative. After I show you, you just know how to do it. You're not estimating anymore. You're finding the exact number every single time. All right. First, let's try to find the indefinite integral. So we're going to first change that into a fractional exponent. Integrate. All right, so go ahead and integrate 3x to 1/2. Okay, so integral of 3 and 3x and 1/2 is what?
2x to the 3/2 plus c.
Okay, good. 2x to the 3/2 plus c. However, there are bounds on this from 1 to 4, so we're not actually going to have a plus c anymore. So we're going to evaluate from 1 to 4. So that line means evaluate. So we're going to apply FTC part 1. FTC part 1 says if you have an integral of this whole thing, it's the same as the antiderivative, which is that function, 2x to the 3/2 of b minus a. So 2, 4 to the 3/2 minus 2, 1 to the 3/2. So this is exactly the application of FTC part 1. Okay? FTC part 1 says if you have this thing and you're trying to figure it out, it's the antiderivative evaluated at b minus the antiderivative evaluated at a. So we're going to figure that out. Okay, 2 times 4 to the 3 halves.
16.
Altogether.
Altogether 16, yes. Okay. Minus 2. So 14, yes. So from now on, you're going to evaluate it by hand, not using approximation, not using Riemann sum for the most part. Yeah, of course, yes.
Why didn't we just do this?
So do we have to worry about like all the other stuff that we learned?
You do, because it's going to come up on the test. It's just they're all leading up to this part.
Okay, but on test, can we use this?
Depends on the question. If it says Riemann sum, you have to use Riemann sum.
Okay.
All right, let's try this one. Okay, so again, we're applying FTC part 1. So you're going to find the antiderivative, the indefinite one, and then you're going to evaluate it from 1 to 2. Do you need me to show you, or you guys can do it? You can do it? Okay. Okay, let's make sure that we're all on the same track. What is the antiderivative?
1/3 x cubed minus 3x.
Good. All right, we're going to evaluate it from 1 to 2. So that means 1/3 2 cubed minus 3 times 2. Let me finish writing and then I'll answer your question. Minus this whole thing. 1/3 1 cubed minus 3 times 1. All right, question.
Why isn't there a C?
Why isn't there a C? When you have a C, so you only have a C when there is no limit. So if you just have x squared minus 3 dx, you would have 1/3 x cubed minus 3x plus c, because you don't know what the initial value is. Okay. However, when you apply FTC part 1, you actually ignore that c altogether because you could go straight to this part.
Got it.
Yeah. Okay, so this part is probably the part that everyone gets stuck on, this minus bracket. Please keep your signs straight. Okay, please be really careful. It's just, the calculation that's going to trip people up. Anyways, those of you who finished, what number did you get? Good. All right. C. Again, you have to memorize what inverse secant square is. If you don't, then that's kind of impossible to calculate. Integral of secant square. Yes, tangent. Okay, answer is 1. Good. All right, now let's go ahead and try something with just variables. What is this? Apply FTC part 1. Huh?
Are we going to have an A value though?
We don't have an A value, so you're going to write in terms of A.
Yeah, that's
FTC part 1 says
Oh.
big F.
A? Yeah.
Yes. Uh-huh. Yes, that's it.
Yeah.
There's nothing you can do. You don't know what A is.
okay, so we just leave it like that.
Yes, correct.
That's it?
Yes, that's it. Number 2, e to the x. Yes, question.
If you do like multiple antiderivatives, you have like big F prime or something like that?
They will usually start with if you have 2 integrals, then they will usually give you the function as f double prime. So you go back to the original, because I don't know what it would be if you take another antiderivative of big F. Yeah. Okay, what's number 2? Good. That's it. All right, next. Calculator practice. Okay, we're going to practice using the calculator. So let me show you where the integral button is.
Is it integral button?
There is an integral function built into your calculator. So click on the math button. Math button, and then you're going to scroll all the way down to the bottom, which is number 9, I think. It says FNINT. So function, integral, or whatever that is. You just type the exact thing in your calculator, and you're good. So it looks just like your integral. So,
6.
hmm?
It's d of x over x.
So,
Oh,
okay.
it's 1 over x.
Yeah.
Got it.
What?
Oh.
Okay, so you're gonna type in 3 to 6, 1 over x, x, like that. And it's gonna give you the answer, so really fast.
Whoa.
Just a practice.
So basically,
0.
Wow.
All right, answer is 0.693. Remember to round to the third digit. All right, let's have you try another one. When it says you just use x. Doesn't really matter.
major calculation.
All right, what's your answer? 167, yes. All right, number 3. Okay, number 3, we have a split integral, piecewise function. From 0 to pi over 2 is this. From 0 pi over 2 to pi is this. Sorry about doubling this up. I forgot to double check. So you need to split up your integral. So from 0 to pi over 2 is sine. From pi over 2 to pi is cosine. Okay, try it.
So do we just find one and then find the other?
Yeah, so you want to just split it. So,
Is this no calculator one?
oh, yeah, definitely.
No problem.
Oh, yeah.
No problem. Nice number.
Okay, so you can do this integral in your head pretty easily and evaluate. It's just everything in the first quadrant. So do that. Let me know when you have the answer. All right, this is 0. All right, now let's look at a different example. 0 to 2 of this absolute value. We've never really dealt with absolute value before. So let's kind of think about it. 2x minus 1. 2x minus 1 absolute value. Can you imagine how this graph looks like? It's a V. Where does the vertex go? Huh? 1/2. So the graph is going to look like this. And we're trying to evaluate from 0 to 2. So it's going to be this area. Okay, so just kind of imagine in your head for now. I'm going to show you how to do it without any kind of graph. So when you evaluate, you can't really just take an integral of an absolute value, because if you do, you're just doing 2x minus 1, which is this graph. Right, so now if you just integrate like that, you're going to have a negative area, which is not okay. Does that make sense?
0 to 1/2 and then 1/2 to 2.
Yes, so then you need to split up the integral. You need to split up the integral where the flip happens.
Wouldn't it still end up doing the same thing?
You would do the same thing, except remember, if you were to do 2x minus 1, then your integral area is going to be positive here but negative here. So you're actually going to subtract it out. So you need to take care of,
Split it.
right, split it so then you make both of them positive. Okay, so now how do you know when it's going to flip over?
What is 0?
Yeah, when it's 0. So make it equal to 0, and then x is equal to 1/2. So now we know it's going to flip over at 1/2. So then you would split this integral, 0 to 1/2, 2x minus 1 dx plus 1/2 to 2, 2x minus 1 dx. But this is still not correct. Can you guys tell me why?
Because that's negative.
Yes, I didn't change this integral function, right? I'm still using 2x minus 1, so one of them is still negative, right? So it's still a problem. So what I like to do, because this is a very simple question, when you get to a graph where there are polynomials and their absolute value on the polynomial, for me, it's very hard to tell which one is below, which one is above. So what I do is I just say everything is positive. Just kind of brute force. Make everything positive no matter what that number is. I don't want to figure out if it was negative or positive. Just make it positive. So, sorry, I don't have a clever way. So I just do that, and then I find the
very
number.
effective.
Yeah, we're
Okay, so anyways, this is a little bit long to solve, so I'm gonna just know that you guys can solve this on your own. But what I do want to talk about is the difference between some absolute value notations. For example, I just wanted to talk about the absolute value notation. So, okay, so absolute value x. Is this the same thing as this? Sorry. Are they the same thing?
No. No, they're different functions.
Okay, talk.
I mean,
Just make everything positive like that. That's what every number positive.
Okay, so talk to the person next to you. Are they the same thing?
No, they're not the same thing. Actually,
Okay, raise your hand. If you think they're the same, raise your hand. If you think they're not the same, raise your hand. Okay, they're not the same. So let's go ahead and think about how it is, how it looks like. All right, so the very basic function is just x, right? So this graph is just like this. All right, so when you make an absolute value on the x, that means you can only have positive numbers. So then this other part flips up. That's why you get an absolute value, right? It cannot be negative, must be positive, so you get a v. So then if you were to find the integral, you would find whatever it is, but you're only going to have positive numbers. Yes?
yeah.
On the right-hand side, you have this other one. When you have a x is now your function, you're making the result positive. The result positive. So the result is going to be this part plus this part. Whatever the result is, you make that positive. So they're not the same. One of them, you take all the area and then you make them all positive and add it together. The other one, if it's negative, it becomes positive. If it's positive, it still stays positive. But the problem is the two area may subtract each other and you may get less value area. Okay? They're not the same. Please be careful. Okay. All right. Practice. Okay, where does this graph flip over? 3. Because that's when this is equal to 0. There's another number that flips over, right? Negative 3, but not within the interval. So we don't care about that. So 0 to 3, x squared minus 9 dx plus 3 to 4, x squared minus 9 dx. And I'm going to be a little bit, just make everything positive. Any question on this one? This is very important. Yes? Yes, you would. Yes, you would. But then I just tried to. Because I already split up the interval. If I didn't split up the interval between the negative part and the positive part, and then I know where the graph is negative, switches from negative to positive. So then I forced this part to be its own interval, and then I flipped it up. So then it doesn't matter.
It doesn't matter.
Yes, you just cannot put an absolute value. Like you cannot do this. Yeah, because now you're taking the sum of those positive and negative and then make that positive, so that's not it.
Is it
35, no, it is not a whole number.
Oh, I'm so stupid. What's 9 times 4?
36.
It's fine. So it's 36?
No,
No.
it's a fraction. Hmm?
Oh, wait. Is it like
Yes.
wait.
Huh? No, it's positive. It has to be positive.
It's fine, right. Is it positive?
Hmm? No. Okay, for the sake of time, 64 over 3. It has to be positive. We made everything positive.
Well, that's what we got. Oh, that was okay.